Hey you all. So in this video, we're going to learn how to differentiate inverse functions. Before we dive in, here's a little review of some of your summer homework, which was objective 0.5.1 and really all of objective 0.5. So if you want a deeper review of inverse functions, check that out. But reminder that there are three and actually more ways to determine if two functions are inverses of each other. The first one is if we graph both those functions, they are symmetrical across the line y equals x. So if I flipped and mirrored one across that line, it would be an exact match to each other. Two, the input-output relationship of one function is the same as the output-input relationship of the corresponding function. So if I had like f of 2 equals 5, and f of x and g of x are inverses, then g of 5 equals 2. And I'll show that off in a second. And then if one function is inputted into the other function, as you're seeing right here below, the result is x. And that is going to be how we actually start finding the derivative of inverse functions. Before I dive into that, let me show off these principles. So first of all, you can see pretty clearly that functions natural log of x and e to the x, which are inverse functions almost by definition, you can see that they are in fact inverses because they are symmetrical across this line. I'll show you a picture in a second to kind of further show that off. Also, if I highlight the point right here, 1, 0, we can clearly see the point that almost matches right across that line. If we drew a straight line perpendicular to y equals x, it would match straight to that point. You can see it has the opposite input-output relationship. And then lastly, let's say I defined a function h of x as equal to, I'll say, f of g of x. So setting them up as a composite function, if I plug one function, g of x, into the other function, f of x, we can see that it does indeed map directly to the line y equals x. What's cool is if I now plug in like h of 2, it equals 2, thus proving like that it does equal this relationship of like when I plug in an x, I get that corresponding y. And I could even do h of -4 to show off that, yep, this is showing a pretty strong inverse function example. So let me pause real quick. Now here's that same graph we just saw, and I literally just turned it on its side so we could see that e to the x over here, I'm going to use the laser, you can't see it all that well, but e to the x over here is in fact an exact mirror to natural log of x over here. And so let's actually get into the core of this objective, which is how do I differentiate if I know functions are inverses of each other? And this is a really classic popular AP type question where they'll do this. Well, they'll say we have some function f of x, and then you're told that the function f of x is an inverse function with g of x. So they are inverses of each other. And then you're being asked to figure out what is the derivative of f of x given only a little bit of information about g of x. So it's really tempting to be like, how do I even do that? And it starts with this relationship right here. What I'm going to do is find the derivative of this relationship, which, a reminder, this is true because we know that f and g are inverses because we were told that. Like we were told that to start this problem, and we'll analyze these in a second. But if I start with this initial relationship and I want to find the derivative, well, this is actually going to involve the chain rule. It's actually technically also going to involve implicit differentiation, but because all of my input values are just x values, I don't have to worry about the implicit part. If this was f of y, then I'd also have to use implicit differentiation and have dy dx's built in. But let's start to derive this. So on the left side, I have g of f of x. So if we imagine, again, like an outer function g, the way we start to derive this is saying, okay, whatever the derivative of g of x is, with that same f of x input, and now times the derivative of the inside function, f prime of x. And now if we derive on the right side of the equal sign, we get 1. Now, reminder, we actually did just use implicit differentiation. If I found the derivative of the inside function x with respect to x, that's just 1. So I could have written times 1, but that's not going to change the function. And that's why we don't bother with implicit differentiation if we're deriving with the input variables all respect to the same input variable. It's just not needed there. And now what I can do is just solve this function. Like I was curious to know in the beginning, like what is f prime of x? Had to make that clear. Like that's the prompt we were kind of going through. And so now all I need to do is take this expression and just isolate this term right here, which I can do just because all this is multiplying. I can just divide both the left and the right side of the function by everything that's multiplying by f prime of x, so that cancels. And so what we're arguing is this really interesting expression of the derivative of f of x can actually be defined as 1 divided by the derivative of g of x with whatever f of x value in question we're curious about. So if I wanted to know, for example, like what is the slope, I guess I'll do erase, it makes sense. What is the slope on the f of x function of f of a? Well, all I would do is plug in 1 divided by, whatever that f of a value is, that y value, and then I would input that into the g prime function, and that would actually tell me the exact slope at a certain value. Now, that was too abstract for you. We could wonder about like f of 2. And I could use this relationship to figure out what is the exact slope on the f of x function when x equals 2. So that's how this, put x's back for now. That's how this relates to, I guess, the chain rule. And this is how we can differentiate inverse functions. Let me pause and think. Now, I want to quickly show off how this actually does work in practicality too. So let's remind ourselves that f prime of x, if we're dealing with the original inverse functions we started with, f prime of x, the derivative of e to the x, is that coolest function. It is just e to the x. And then g prime of x, the derivative of the natural log of x, is just 1 over x. So that expression defines the slope anywhere on the natural log function. So let's again just prove real quick that these are in fact inverse functions. If I did g of f of x, this should output to x. And so if I took the natural log function, but instead of plugging in x, I actually plugged in e to the x. Reminder what natural log is. It's just log base e. So this question is literally asking, e, so what power would result in e to the x? And that could only be if the question mark, that missing piece, is equal to x. And so that's why you see like natural log and e's cancel each other out, because they're always just going to equal whatever is currently in the exponent of e. And so this expression would simplify to be x. And so that they do indeed evaluate again to be inverse functions. So now I'm curious to know, like, if I actually plugged in, if I was wondering, okay, does this expression hold true based on two functions we know are inverses? Well, let's see if they do. We know that f prime of x is e to the x. And so we're wondering, if I plug in all that I know, does this actually evaluate to be e to the x? Well, the derivative of g of x is 1 over x, and it looks like I'm inputting the function e to the x. So instead of writing 1 over x, which would be the derivative of g of x, natural log of x, let me actually put in that input e to the x. So let me do a little bit of simplifying reminder of some math language. This is 1 and then divided by 1 over e to the x, and that's going to be 1 times dividing is the same as multiplying by the reciprocal, so it's just 1 times e to the x divided by 1. So it really does evaluate exactly to the derivatives that we know are true. And that's what's so cool about this. Starting with just this initial truth, which we know that is true, if we're being told they're inverse functions, we can actually figure out slopes on either function just with that base knowledge of, hey, these are inverses. You actually do know now, you now know a lot about being able to calculate slopes on the opposite functions. So a few takeaways. If we are told functions are inverses, we know two important AP calculus math facts right away. We know that this is true. We know that if I'm plugging one function into the other, they always evaluate to be x. And that means by going through and like actually applying the chain rule derivative, I can figure out an expression that can help me find the slope at any given point on the original function, even if I don't know how those functions are defined. I don't want to go through and do this for you because it's going to come from video. So if you have questions about how I got to this expression, please ask, okay? And then a reminder about the other really important, and I put B, so this is like number 1 cool math fact, and then this is number 2 cool math fact with B, is that if f of a equals b, then g of b equals a, which just means the input-output relationships are opposites if we know they are inverse functions. And so if I have like one example problem, f of x and g of x are inverses. If f of 2 equals 0, then g of 0 has to equal 2. So keep that information in mind as you dive into videos in this objective. That's going to be really helpful.